Hi class, today we are going to talk about trigonometry. This is just an introduction as it's the first day of the chapter. Our objective today is that I can find trigonometric ratios in a right triangle with no side lengths. So we're going to be talking about when we have the sides, I can find these special ratios. Before we really get into the meat of the lesson, we need to make sure we understand some language around triangles. All three of these, first of all, are right triangles at the top of your paper. Remember right triangles because it's got this little box in the corner. We also need to be able to label the sides by name. The first name we should recognize is hypotenuse. And the hypotenuse of a right triangle is the side opposite or across from the right angle. So in triangle ABC, this would be my hypotenuse. Take a second and label your other two triangles. Hypotenuse DEF, it should be this one because it's across from the right angle, and in GHI it would be this side length. The other two sometimes are a little more confusing for students. The next one we're going to talk about is the adjacent leg. Now both these other ones are called legs because they are not the hypotenuse. So in ABC the two blue sides are called legs. The adjacent leg is the one that is touching the angle that you're talking about, but not the hypotenuse. So in this case, this leg right here is touching the 33-degree angle, which is the angle that we're discussing in this part of the unit. So this side is called the adjacent. Take a second again, and on your own, try to find the adjacent and the other two. Pause it if you need to. And in this case, it should have been this leg and this side. And finally, the opposite side is the one that's furthest from the angle you're talking about, which again in this case is that 33-degree angle. The other way I like to think about it, it is in fact opposite or across from that angle. Okay, so label those in your triangles as well. Now as part of today's lesson, we were going to take some time to measure these side lengths, but I don't want to, since I was gone, I didn't want to take your time to mess with the rulers and stuff, so I'm just going to give you what I got when I labeled these. After I get these all down, make sure you pause it if you don't have them written down yet. So the adjacent of my first triangle was 3.7 centimeters. The opposite is 2.4 centimeters, and I got the hypotenuse to be 4.4 centimeters. In the second triangle, I got the opposite to be 4.1 centimeters. The hypotenuse to be 7.5 centimeters, and the adjacent to be 6.3 centimeters. And finally, in my third triangle, I got the hypotenuse is 3.0 centimeters, opposite was 1.6 centimeters, and the adjacent was 2.5 centimeters. So again, pause this for a minute, make sure you have everything that I have labeled in the top three triangles labeled on your paper as well. Because now we're going to use those measurements and talk about three different ratios within those triangles. We can easily see that the side lengths are different, but we know that the angle measures are the same because we've given you 33 degrees in all three cases. So we'll do the first triangle together. If I have triangle ABC, I'm going to now calculate the opposite divided by the hypotenuse. And that's what's helpful, that I have both the names of the side lengths labeled and the numbers, because now I find the opposite of the first one, which is 2.4. That's going to be the top of my ratio, divided by the hypotenuse, which was 4.4. We are going to type those into our calculator and round to 3 places, as it says here. And I got about, so I use a squiggly equal sign when I say about, 0.545. Now going across from the same triangle, I'm going to find the adjacent length, which is 3.7. divided by the hypotenuse, which is 4.4. So again, I'm finding this ratio of this triangle. When I type that in my calculator, I get 0.841. And finally, from that same triangle, I'm finding opposite over adjacent. The opposite we said was 2.4. The adjacent length was 3.7. Type it in my calculator, and I get 0.649. So take a second, pause this video, and calculate those same three ratios for the second triangle, DEF, and then your third triangle, GHI. I'm going to quickly write out what I got when I did it. For this one, for the middle triangle, opposite over hypotenuse, I got 4.1 over 7.5. I typed it in, I got 0.547. The adjacent in that triangle was 6.3 over the 7.5 hypotenuse, which gave me about 0.840. And finally, the opposite was 4 over the adjacent of 6.3. It's about 0.651. Finally, my last triangle, I might have been a little off in my measurements. I probably should have gone back just to double check it. 1.6 over 3.0. I got about 0.530. The adjacent over hypotenuse, I got 2.5 over 3.0, which is about 0.833. And finally, I got 1.6 over 2.5, which is about 0.64. Okay? So now the next question is, what do you notice about these numbers? I'm not going to write anything down, but we are going to talk about it. When I say, what do you notice about these numbers, I'm going to talk about one column at a time. Now remember, when we look at those three triangles, we can clearly see their different sizes. However, their angle measures are the same. So when I'm comparing these ratios, opposite over hypotenuse, we can see that 0.545, 0.547, 0.530. Again, this one's a little off, but you can see they're very close. In fact, if I round all three of those to the nearest tenth, I get 0.5. We can see the same is true for adjacent over hypotenuse. When I divided all three of those, if I round these all to the nearest tenth, I get 0.8. And the same thing happened in the third column. Again, if I rounded them to the nearest tenth, I get 0.6. I guess I'd get 0.7 for that second one. But you can see they're very, very close. And that's not a coincidence. The side lengths of triangles that have the same angle measure, even though the lengths of the sides are different, they maintain these same ratios. And we can use this concept to find different side lengths when we know some of the side lengths of a triangle. For example, if we look at this next part, it says, talk to your group about how you could use the information in your table to find the missing side of this right triangle. So again, I know this angle is 33, so we're still talking about the same thing we've been talking about above. I need to label the three sides of the triangle. First, across from the right angle, call that hypotenuse. I usually label this one next. I always go across from the angle and label that opposite. Then by default, the other side is adjacent, but again, it's the side touching that angle that we're talking about. Now in this case, the one side length that I know is the hypotenuse. So since the angle measure is the same, and since in this table above we said that we know that the opposite over hypotenuse was always about 0.545, we can use that idea and say, since we know that opposite over hypotenuse was about 0.545, I probably should have just rounded to 1 or 2 decimal places. We can use that concept, since this is still a triangle with 33 degrees, and substitute what we know. Well, we know that the hypotenuse is 7.64, and now I can just use that and solve algebraically for opposite, just like it was in x. If I had x divided by 7.64, we know we would multiply both sides by 7.64, and I get that the opposite side length now is 4.2 centimeters. So we use this idea, and I can label it over here, we use this idea, I guess if this was centimeters, to be able to solve for missing side lengths, which again was the point or the objective of the lesson. Then I can also do it for the adjacent as well. Again, the second column said that the adjacent over hypotenuse is about 0.84. Okay, so that was kind of the ratio we got in all three cases. Again, I'm solving for adjacent, that's the one I don't know, but they gave me that the hypotenuse was 7.64. I get that's about 0.84. Now in theory, you could say, well, now I know the opposite as well, so could I have used opposite over adjacent? You could have, but since we did some rounding in this in the middle situation, I always default back to the one side length that they give me, because it'll be more accurate. So I'm going to multiply both sides by 7.64 as well, and I get that the adjacent side length then is about 6.4 centimeters. And I can label that. So now I know all the side lengths of that triangle, even though in the beginning I only knew one angle and one side length. Now as we flip our page over, the next piece is we've only been looking at angles of 33 degrees, but it's important to know that's not special just to 33 degree angles. Turns out the ratios you found are consistent for any angle in a right triangle. This fact is so useful that there's a whole branch of mathematics where about studying triangle measures. It's called trigonometry, which is what we said this chapter is about. And it's used by land surveyors to make maps of our world. When you can't get somewhere like the top of a mountain to measure, you can often measure an angle and a distance and draw imaginary right triangles to help you find missing distances. So there's a ton of real-world application with trig. For today, your job is to learn the big three trig ratios that you will use over and over and over again for angles. They're called sine, cosine, and tangent. As we look at them, you're going to start to see this weird symbol. It's a circle with a line through it. That's called theta. And math people like to use that any Greek letter to stand for angles they don't know. So the three ratios that we need to know should look familiar. Again, we're talking about that opposite over hypotenuse. But now we're talking about it. It's called sine of theta equals opposite over hypotenuse. Cosine of theta is the middle one, adjacent over hypotenuse. And we're talking about the side lengths of adjacent and hypotenuse. And finally, tangent is opposite over adjacent. Nice thing is, we have this little acronym because you will need to memorize these, and it's SOHCAHTOA. It helps you remember which one's which. So is the S stands for sine of theta, and it's equal to the OH, which is opposite over hypotenuse. So you do have to remember it's the ratio of those. Ka is cosine of theta equals adjacent over hypotenuse. And TOA is tangent of theta equal to opposite over adjacent. So oftentimes just memorizing those three trig ratios is enough for students or memorizing SOHCAHTOA helps them memorize the three trig ratios. Now let's look at an example of how we use this in any situation. You can see here we don't know what theta is. Our first job is to always label those three legs. So across from the right angle is the hypotenuse. Across